differentiating y equals x squared from first principles. So here we have y equals x squared. And we're going to take a point on here and another point further up because we're going to use a limiting chord argument. So here's the chord that we're going to be using, and we're going to be moving this point here closer to this one down here. This point here is a general point on the curve, so if its x-coordinate is x, because the curve is y equals x squared, the y-coordinate is x squared. Up here we've got x plus h, so what we're saying is from x we're going a little bit across, a distance h. And if x plus h is the x-coordinate, because the curve is y equals x squared, the y-coordinate is x plus h all squared. So what we're interested in is rise and run. And of course this is a right-angled triangle. So this distance is h. That's the difference between the x-coordinates. If we look here, the y-coordinate is x plus h all squared, and down here it's x squared. So this length is h plus h all squared, take away x squared. And that means the difference in the y's, which is the rise, divided by the difference in the x's, which is the run, so delta y means difference in y, delta x means difference in x, is x plus h squared take away x squared divided by h. So it's just rise divided by run. Now we can simplify that by expanding the brackets. And then we can see the x squared minus x squared, so we can cancel those out, leaving us with 2xh plus h squared over h. And we can divide by h, so we'll cancel an h there and one of the h's here, giving us 2x plus h. Just to explain that further, we could split the fraction here and go 2xh over h plus h squared over h. So the h cancels here and one of the h's cancels just there. dy dx, which is the gradient function, is what we're really interested in, is what happens when we take the limit as h tends to 0. Remember, h tending to 0 will move this point much, much closer to this point. So dy dx is the limit as h tends to 0 of delta y over delta x. And we've got this expression for that. So that's the limit as h tends to 0 of 2x plus h, which clearly is just going to be 2x. Now this is consistent with our limiting chord lesson that we looked at before. Because if we consider dy dx when x equals 2, remember before we found the gradient function should be 4, we now have an expression for the gradient function. If we put x equals 2 into it, we get 2 times 2, which is 4. Note that we have alternative notations for the gradient function. If our function is given as f of x, then the gradient function is written as f dashed x. If our function is given as y equals, the gradient function is dy dx.